Welcome to this presentation. In this video, I am going to share with you some of the passive and active micro devices. Microwaves are electromagnetic waves with wavelengths ranging from 1 millimeter to 1 meter or frequencies from 300 megahertz to 300 gigahertz. Let's get started with Schottky diodes. We know that a diode is a two-terminal semiconductor device having a nonlinear VA relationship. This nonlinearity can be exploited for the useful functions of signal detection, demodulation, switching, frequency multiplication, and oscillation. So RF and microdiodes can be packaged as axial or beam lead components or a surface mountable chips or be monolithically integrated with other components on a single semiconductor substrate. And the classical PN junction diode commonly used at low frequencies has a relatively large junction capacitance that makes it unsuitable for high frequency applications. So the Schottky barrier diode, however, relies on a semiconductor metal junction that results in a much lower junction capacitance, allowing operation at high frequencies. So commercially available micro Schottky diodes generally use N-type gallium arsenide material, while lower frequency versions may use N-type silicon. So Schottky diodes are often biased with a small DC forward current but can be used without bias also. The primary applications of Schottky diodes is in frequency conversion of input signal. And since they are constructed using a metal component on one side of the junction and doped silicon on the other side, the Schottky diode therefore has no depletion layer and are classified as a unipolar device, unlike typical PN junction diode where it is called as a bipolar device. And this shows the structure of the Schottky diode, where it consists of a metal and an N-type silicon, and in between a junction which is very small is formed. So a lightly doped N-type silicon semiconductor is joined with the metal electrode to produce what is called metal semiconductor junction, and the width of the MS junction will depend on the type of metal and the semiconductor material used. But on forward bias, electrons move from the N-type material to the metal electrode, allowing current to flow. Thus, current flow through the Schottky diodes is the result of the drift of majority carriers. Since there is no p-type semiconductor material and therefore no minority carriers, and in reverse bias, the diode's conduction stops very quickly and changes to blocking current flow. And the electrons on the N side having a low energy level than that of metal, so electrons cannot pass through the junction barrier that is called Schottky barrier. So in forward bias, the electrons on N side gain enough energy to cross the junction barrier and plug into the metal with very large energy. They are called hot carrier, and the diode is called hot carrier diode. And this diagram shows the VI characteristics of a Schottky diode, which resembles a PN junction diode, but the cutoff voltage occurs before the PN junction diode. And the most important difference between the PN junction diode and Schottky diode is its reverse recovery time. And the diode switches from conducting to non-conducting state, where in an NPN diode, the reverse recovery time can be in the order of hundreds of nanoseconds and less than 100 nanoseconds for fast diodes. Schottky diodes do not have a recovery time as there is nothing to recover from. These are some of the important points about Schottky diode. Schottky diode is metal to semiconductor junction. It is a majority carrier device, unlike normal PN junction diode. It doesn't have a charge storage region that are very fast, therefore it has very fast speed. Semiconductors used is usually N-type, and it is very lightly doped, and it is operated at high frequencies from few megahertz to gigahertz range. And the main applications of Schottky diodes are, it can be used in voltage clamping and clipping circuits, and it can be used for reverse current and discharge protection circuit, and it rectifies high frequency signals in low power TTL logic, and it can be used as a switching device also. So the primary application of Schottky diodes is in frequency conversion of input signal, and the three basic frequency conversion operations are rectification, detection, and mixing. So this diagram shows the conversion operation of rectification, detection, and mixing, and this is the VI characteristics of diode, and this diagram shows the equivalent AC circuit model of a Schottky diode. In a rectifier application, a diode is used to convert a fraction of the RF input signal to DC power, and the rectification is a very common function and is used for power monitors and automatic gain control circuits and signal strength indicators. If the total voltage, diode voltage consists of a DC bias voltage and a small signal RF voltage, then V can be written as V0 into small V0 into cos omega naught t. So the diode current will be I is equal to I0 plus V0 into GD cos omega naught t plus V0 squared by 2 GD dash cos squared omega naught t. This can be written as I0 plus V0 squared by 4 into GD dash plus V0 GD cos omega naught t. V0 squared by 4 into GD dash into cos 2 omega naught t. At GD is equal to 1 by Rj. It is the dynamic conductance of the diode. I0 is the bias current and V0 squared by into GD dash by 4 is the DC rectified current. The output also contains AC signals of the frequency omega naught and 2 omega naught, which are usually filtered out with a simple low pass filter. A current sensitivity BI can be defined as a measure of the change in the DC output current for a given RF input power. Here the V0 squared into GD dash by 4 is the change in DC current, and V0 squared into GD by 2 is the RF input power. So therefore the current sensitivity is then given by beta I is equal to delta IC divided by Pin. So this is equal to GD dash divided by 2 GD into A by W. So that's a unit. And the open circuit voltage sensitivity beta V can be defined in terms of the voltage drop across the junction resistance when the diode is open circuited. Thus, beta V is equal to beta I into RG. In a detector application, the non-linearity of a diode is used to demodulate the amplitude modulated RF carrier. In this case, the diode voltage can be expressed as V of t is equal to V0 into 1 plus m into cos omega m into t into cos omega naught into t, where omega m is the modulation frequency and omega naught is the RF carrier frequency. M is the modulation index. Therefore, the diode current is given by I of t is equal to V0 into GD into 1 plus m cos omega mt into cos omega naught t plus V0 squared by 2 into GD dash into 1 plus m cos omega m the whole squared into cos squared omega naught t. Expanding this equation in the form that which is in the form of a plus b the whole square can be written as a squared plus b squared plus 2ab. So I of t is given by V0 into GD into cos omega naught t plus m by 2 cos omega naught plus omega m into t plus m by 2 into cos of omega naught minus omega m into t plus separating the terms in the V0 squared by 4 into GD dash, so that into 1 plus m squared by 2 plus 2m cos omega mt plus m squared by 2 cos 2 omega mt plus cos 2 omega naught t plus m into cos 2 omega naught plus omega m into t plus m into cos 2 omega naught minus omega m into t plus m squared by 2 into cos 2 omega naught t plus m squared by 4 into cos 2 omega naught plus omega m into t plus m squared by 4 into cos 2 of omega naught minus omega m into t. So this diagram shows the frequency spectrum of this output. And the output current terms that are linear in diode voltage have frequencies of omega naught and omega naught plus or minus omega m, while the terms that are proportional to the square of the diode voltage include the frequencies and relative amplitudes. Like for a frequency of 0, the relative amplitude is 1 plus m squared by 2, which can be seen from the equation, above equation. And for a frequency of omega m, the relative amplitude is 2m. For 2 omega m, it is 1 squared by 2. For 2 omega naught, it is 1 plus m squared by 2. For 2 omega naught plus or minus omega m, it is m. And for 2 into omega naught plus or minus omega m, it is m squared by 4. So the desired demodulated output of frequency omega m is easily separated from the undesired frequency components with the low pass filter. In detector application, the nonlinearity of a diode is used to demodulate an amplitude modulated RF carrier. In this case, the diode voltage can be expressed as V of t is equal to V0 into 1 plus m cos omega m into t into cos of omega naught t. So similarly, when we write the equation for current I of t is given by V0 into GD into 1 plus m into cos omega m into t into cos omega naught t plus v naught squared by 2 into gd dash into 1 plus m cos omega m into t the whole squared into cos squared 2 omega naught t. So that is given by v naught into gd cos omega naught t plus m by 2 into cos of omega naught plus omega m into t plus m by 2 into cos of omega naught minus omega m into t plus v naught squared by 4 into gd dash into 1 plus m squared by 2 into 2m cos omega mt plus m squared by 2 cos 2 omega mt plus cos 2 omega naught t plus m into cos 2 omega naught plus omega m into t plus m into cos 2 omega naught minus omega m into t plus m squared by 2 into cos of 2 omega naught t plus m squared by 4 into cos of 2 into omega naught plus omega m into t plus m squared by 4 into cos of 2 into omega naught minus omega m into t. So the frequency spectrum of this output is given in this diagram. Okay, the output current terms that are linear in the diode voltage having frequencies of omega naught and omega naught plus or minus omega m. So the desired demodulated output of frequency omega m is easily separated with a low pass filter, and you can observe that the amplitude of this current is m into v naught squared into gd dash by 2, which is proportional to the square of the input voltage and hence the input signal power. And the next diode which we are going to see about is the pin diodes. The diode is in which the intrinsic layer of high resistivity is sandwiched between the P and N region of the semiconductor material. Such type of diode is called as pin diode. And the high resistive layer of the intrinsic region provides the large electric field between the P and N region. So the electric field induces because of the movement of the holes and electrons. Now let us see the pin diode structure. The diode consists of P region and N region, which is separated by intrinsic semiconductor material. In P region, the hole is the majority charge carrier, while in the N region, electron is the majority charge carrier, as we all know. And the intrinsic region has no free charge carrier. It acts as an insulator between N and P type region, and the I region has a high resistance which obstructs the flow of electrons to pass through it. And this is the structure of the pin diode. And when the diode is kept forward bias, the charges are continuously injected into the I region from the MP and N region. So this reduces the forward resistance of the diode and behaves like a variable resistance. The charge carriers which enters from the P and N region into the I region are not immediately combined into the intrinsic region. The finite quantity of charge stored in the intrinsic region decreases that resistivity. So pin diodes can be used to construct an electronic switching element, and it can be easily integrated with the planar circuitry and are capable of high speed operation. Switching speeds typically range from 1 to 10 microseconds, and pin diodes can also be used as power limiters, power modulators and variable attenuators. Pin diodes contains an intrinsic layer between the N and P-type semiconductor layers. When reverse bias, a small series junction capacitance leads to a relatively high diode impedance, while a forward bias current removes the junction capacitance and leaves the diode in a low impedance state. So these characteristics makes the pin diode useful for RF switching element, and the parasitic inductance is denoted as Li, and the reverse resistance is denoted by R. So this diagram shows the single pole pin diode switch. A pin diode can be used in either series or shunt configuration to form a single pole, single throw RF switch. That can be seen in this diagram. So in this series configuration, the switch is on when the diode is forward biased, while in the shunt configuration, the switch is on when the diode is reverse biased. So in both cases, input power is reflected when the switch is in the off state. And the DC blocking capacitor should have a relatively low impedance at the RF operating frequency, and the RF choke inductor should have a relatively high RF impedance. An ideal switch would have zero insertion loss in the on state and infinite attenuation in the off state. Realistic switching elements, of course, result in some insertion loss for the on state and finite attenuation for the off state. So this diagram shows a simplified equivalent circuit for the series and shunt single pole pin diode switches. When the first diagram shows the series switch and the second one is the shunt switch. So we can define the insertion loss in terms of the actual load voltage VL and V0, which is the load voltage that would appear if the switch is absent. So IL, insertion loss, IL is given by minus 20 log of VL divided by V0, the modulus value of VL by V0, right? So for a series switch, IL is given by minus 20 log of modulus of 2 Z0 divided by 2 Z0 plus ZD. Whereas for a shunt switch, it is given by IL is equal to minus 20 log of modulus of 2 ZD divided by 2 ZD plus Z0. In both cases, ZD is the diode impedance for either the reverse or forward bias state, and thus ZD is the ZR that is equal to RR plus J into omega Li minus 1 by omega CG for reverse bias, whereas ZF is given by RF plus J omega Li for forward bias. The on-state and off-state insertion loss of a switch can usually be improved by adding external reactance in series or in parallel with the diode to compensate for the diode reactance. So this technique usually reduces the bandwidth. So several single throw switches can be combined to form a variety of multiple pole and multiple throw configurations. And this diagram which shows the series and shunt circuits for a single pole double throw switch, and such a switch requires at least 2 switching elements. In operation, one diode is forward biased in the low impedance state while the other diode reverse biased in the high impedance state. The input signal is switched from one output to the other by reversing the diode bias states. The quarter wave lengths of the shunt circuit limit the bandwidth of this configuration. So this diagram shows the single pole double throw pin diode switch. Thank you.